Alright, silly people, here's the situation. We have a time-dependent wave function given there, and we're meant to find the normalization constant A, as well as the expectation value of position, the expectation value of position squared, the standard deviation, um, and then plot it. Um, so let's do the normalization. So we know that the integral over all space of the square modulus of this wave function over position is equal to 1. Uh, we do have some complex terms, so I have to specify that it's psi star psi dx. So in all, that's going to be, there's going to be an a squared out front. You're going to have e to the minus lambda absolute value of x, e to the I omega t, e to the minus lambda absolute value of x, e to the minus I omega t dx equals 1. And so the imaginary components will cancel out. You'll just have a squared integral over all space of e to the minus lambda x dx. That's minus 2 lambda dx, sorry. Minus 2 lambda absolute value of x dx. That integral has a standard form. It results to being 1 over lambda. So that has to equal 1, so we find that a squared is equal to lambda, so a is just root lambda. Cool. Then the wave function, now that it's normalized, we'll root lambda e to the minus lambda absolute value of x e to the minus I omega t. Then the expectation value of position will just be the integral over all space x modulus squared of the wave function. So now we're doing lambda out front, integral over all space of e to the minus 2. I have an x out front here, e to the minus 2 lambda absolute value of x dx, which is 0. You've turned an even function into an odd function, so that's just 0. The expectation value of position squared, though, being x squared times the square modulus of the wave function, will be lambda integral over all space of x squared e to the minus 2 lambda absolute value of x dx, 1 over 2 lambda cubed, so you have lambda over 2 lambda cubed, simplifying a bit, 1 over 2 lambda squared for your expectation value of x squared. Now the standard deviation will just be the square root of the expectation value of position squared minus the squared expectation value of position, which is, we found this to be 1 over 2 lambda squared. That was 0. So you just have 1 over lambda times the square root of 2 for your standard deviation. Also, the problem asks for the probability that you find the particle in between, or actually outside of the region described by minus lambda to positive lambda. If this was a Gaussian, I could tell you right now that it would be 32%, but it's not quite a Gaussian. So the probability that you find the particle between negative infinity and negative sigma plus the probability that you find it between positive sigma and infinity, by definition is equal to 1 minus the probability that you find it in between minus sigma and sigma. So that means we only have to do one integral. So we're just doing the integral from minus sigma to sigma. Don't know why I'm writing it like that. Minus sigma to sigma of the square modulus of the wave function. So you have 1 minus lambda times the integral of from minus sigma to sigma of e to the minus 2 lambda absolute value of x dx. That integral is a little bit non-trivial, so you have to split it up into a couple of different regions, which are from minus sigma to 0. You're going to have to turn the fact that we have an absolute value into minus x dx for just the region for 0, and then you'll have this 0 to sigma where this works as normal as just minus 2 lambda x dx, right? So you have 1 minus lambda times just from minus sigma to 0 e to the minus 2, not minus 2, so 2 lambda x dx. And then on the other side, you have the result of that integral as being minus e to the minus 2 lambda x over 2 lambda, evaluated from 0 to sigma. And then the first integral now will evaluate to e to the 2 lambda x. Let me use a parentheses here, over 2 lambda from minus sigma to 0. And then we can go ahead and plug stuff in. So we'll have 1 over 2 lambda. We're going to have a minus sign actually. Minus 1 over 2 lambda. It's minus 2 lambda, and then sigma was 1 over lambda root 2. So we have that kind of thing going on there. Lambda root 2. And then the exponent of 0 is just 1. So you have plus 1 half. 1 over 2 lambda even. Right? Just keep on trucking. We have an exponent raised to 0, so that's just 1 over 2 lambda. And we have e to the minus 2 lambda over, 2 lambda over lambda root 2. Cool. And then we still have this guy. This also has to be divided by 1 over 2 lambda. Almost missed that. And then, okay, minus 1 over 2 lambda exp minus 2 lambda over lambda root 2 plus 1 over 2 lambda. So everything has a lambda term, so we can cancel out the lambda out front. And then everything seems to be multiplied by 1/2, but actually these terms match and these terms match. So actually we're just going to add them up inside the parentheses, and we'll have 1 minus 1 over, it's just 1 minus e to the minus root 2. What I have here now is a Desmos plot of all of the relevant quantities in this problem. So, okay, so there's the wave function. Clearly not a Gaussian. It has that weird peak. The peak does occur at y is equal to L. It's centered at 0. And then we have, I've shaded in the regions that the problem is asking for, the probability that it lies in between those points. And then the region in between is not shaded in. And so here I have the actual integral from negative infinity to negative sigma, positive sigma to infinity of the square modulus of the wave function that Desmos is doing numerically, and it perfectly matches our result for the probability there, no matter what value L takes. So that's kind of what the wave function will look like.